So we would like to discuss what it means to have a norm on a vector space. So in order to get started, let's suppose that V is a vector space. So let V be a vector space over the real numbers. Then a norm on that space is pretty much the analog of absolute value for real numbers. It's a way to measure the length, the magnitude of the vectors, and also to measure distances in that vector space. So then a norm on V is a function. So we're going to denote it with two lines like this. So it's defined on V and takes values in R. And satisfies the following properties. So first of all, it's greater than or equal to 0. So the length, the norm of any vector is greater than or equal to 0 for any u in V. Secondly, the only way this can be 0 is if and only if we have the 0 vector. The third property is that it behaves quite nicely with respect to scaling of vectors. So if you scale a vector and then you want to find its norm, it's the same thing as if you take the norm of the vector and you multiply it by the absolute value of the number lambda. So here we said that we are in a vector space over the real numbers. So this would be for any u in V and any lambda in R. And the last property is the so-called triangle inequality. So if you take the sum of two vectors and you take their norm, then that cannot exceed the sum of the norms. The reason we call this the triangle inequality is if you have a triangle, and you can always think of this in terms of vectors. So here are two vectors u and v that add up to u plus v, which is this one. And then what we're saying is that the length of the sum is cannot exceed the sum of the lengths. So that's why we call this the triangle inequality. Now, we said that obviously we can measure distances in a vector space by using a norm. And so distance between u comma v is precisely the norm of their difference. That's exactly what we do in the real numbers. The distance between two real numbers is precisely the absolute value of their difference. It would be a good idea to give some simple examples. And the simplest examples one can give are norms in Rn. So let's recall that Rn is a set of all n tuples of real numbers. And let's start with maybe the one norm that it's the simplest to verify that it's a norm. Sometimes we call this the one norm. So to a vector space, to a vector x1 up to xn, the one norm is simply the sum of the absolute values of the coordinates. In fact, it's almost trivial to verify that this definition satisfies all the four properties that a norm should satisfy. Then we have the classical two norm. which is simply the sum of the absolute values squared. And then we take the square root of that. So that's the usual. So for example, in R2 or R3, that's the usual Euclidean norm. And it reflects the normal way of, or the standard way of measuring distances in everyday life. Of course, somebody here might note, why do I use absolute values? It seems redundant. I mean, I could have certainly written this way, which looks much simpler. Or I could have put a square root, right? I mean, all of these things are the same. But there's a very interesting reason why I use this notation. And the reason is that we said from the very beginning that we're working over the real numbers, right? I mean, we can do very similar things over the complex numbers. And if you were to define this norm over the complex numbers, then this expression here would not be the appropriate one, because these numbers, the sum that you would get here would not even be a real number. So you would need absolute values in the case of complex numbers. So that's the only reason why I use this notation. And then there is a formula that, or a norm for that matter, that really generalizes both of the above ones. It's called the P norm. And here we take the absolute values, we add up their pth powers, and then we take we raise the whole sum to the power 1 over p. So for p equals 1, we get the 1 norm. For p equals, we get the 2 norm. And here, in general, we want p to be greater than or equal to 1. Finally, I would like to indicate one more norm that is quite common in this context for Rn. And that's the so-called infinity norm, where we simply take the maximum of all the xi's for I equals 1 to n. Even though, like I said, for the first norm, it's a trivial matter to check that it's a norm, it would be nice to do so. These norms, it's not such a trivial matter. So in fact, we have some inequalities that establish that these expressions are norms, that actually bear the names of their creators. So it's certainly not a trivial matter, and we will come back to this at a later video. But for the moment being, that's what a normed linear space is. So it's a vector space equipped with a norm, which is a way of measuring the vectors in that space. Thanks for watching.